Welcome to part 2 of my talk on Unbinding Prometheus, how generative AI liberates computational thinking from coding. In part 2, I explain what computational thinking is and how it focuses on structuring problems for humans and/or machines to perform, not about traditional coding itself. I also describe how generative AI is decoupling computational thinking from programming syntax, shifting from the how of coding to the what of intent, so that anyone, from poets to scientists to doctors to musicians, can reason computationally through prompt engineering and its complementary discipline, context engineering, rather than through manual programming. Now that we've walked through several examples of no-code applications of generative AI, let's step back and talk about what computational thinking actually is and why it matters. About 20 years ago, Dr. Jeannette Wing, then a computer science professor at Carnegie Mellon University, wrote a landmark article in the Communications of the ACM magazine defining the term computational thinking and positioning it as a universally applicable attitude and skill set that everyone, not just computer scientists, would be eager to learn and use. She later went on to serve as Assistant Director for Computer and Information Science and Engineering at the National Science Foundation, Vice President of Research at Microsoft, and is now Executive Vice President for Research at Columbia University. Dr. Wing described computational thinking as the mental framework for formulating problems so their solutions can be represented as computational steps or algorithms. She viewed it as a way of analysis and reasoning that transcends coding itself, an intellectual toolkit that students, scholars, and professionals in every field could embrace to solve complex problems more effectively. 5 core elements of computational thinking are shown on this slide. Logic is about reasoning through problems step by step, evaluating what's true, what's false, and what follows from the evidence. It's how we teach machines and ourselves to make sound and consistent decisions. Decomposition means breaking a big, messy problem into smaller, more manageable pieces. Once each piece is solved, they can be reassembled into a complete solution. Spotting patterns, similarities, and regularities across problems enables us to reuse ideas and accelerate our problem solving. Automation is the engine of execution, where our reasoning becomes a process that machines can perform, turning logic into action and freeing us to focus on creativity and innovation. And finally, abstraction is the art of focusing on what truly matters by filtering out the noise, highlighting the essentials, and modeling problems in ways both humans and computers can understand. Together, these 5 elements form the foundation of computational thinking, the mindset that powers both coding and creativity in the age of AI. It's important to recognize that computational thinking isn't limited to coding. Instead, it's about thinking systematically, turning complex problems into structured, repeatable processes that humans and machines can perform, either together or separately. Over the past 2 decades, however, the practice of computational thinking has largely involved writing code, usually in second and third generation languages like C, C++, Java, and Python. But as every computer science student, faculty, and professional knows, fluency in these languages often means wrestling with accidental complexity rather than focusing on meeting actual domain requirements. Programmers must contend with syntax and semantics, memory leaks, concurrency bugs, buffer overflows, off-by-one errors, and headaches associated with error handling and distribution. Speaking as someone who spent decades deep in that code, both as a teacher and a programmer, I know from experience that many of these struggles are self-inflicted. It doesn't have to be this hard to think computationally. We've just mistaken these accidental complexities for necessity. If you trace the history of automobiles, you'll see the same curve we're riding now in computing, the shift from the how to the what. 120 years ago, if you wanted to drive, you first had to build the car yourself. Every bolt, belt, and spark plug painstakingly assembled by hand. 70 years ago, to drive a car, you needed to know how to maintain it by changing the oil, tuning the carburetor, and hoping it started on cold mornings. Today, driving has gone mainstream. You don't need to build or fix the car. You just need to operate it and fuel it or plug it in. And soon you won't even have to drive. You'll simply tell the car what destination you want to go to, and it will decide how best to get you there. I saw that future firsthand on a recent trip from Franklin, Tennessee to the Nashville airport. My Uber driver set his Tesla on autopilot and then never touched the wheel, accelerator, or brakes the entire 30-minute ride. It was equal parts thrilling and unnerving, like watching the future flex its muscles. But it worked. I arrived alive and deeply aware that autonomy is no longer science fiction, it's a beta feature. Just as the steering wheel is giving way to the algorithm, computing is also now shifting from the how to the what, from mechanical construction to expressive intent. 70 years ago, if you wanted to use a computer, you had to build it from scratch, solder the circuits, punch the cards, and pray your program would compile before sunrise. When I learned to code 40 years ago, we worked in third-generation languages like Pascal and Ada, painstakingly tracing through printouts and manually debugging logic by sheer force of will. Believe it or not, some universities still teach introductory programming that way. But the world has moved on. Modern software development is less about handcrafting every line and more about composing, assembling systems, connecting frameworks, and orchestrating application programming interfaces. Ironically, many academic programs still underplay this reality. Now we stand at another threshold. Soon you won't need to write much traditional code at all. You'll describe what you want in natural language, and your development environment, powered by large language models, will generate, adapt, and even test the solution alongside you. The level of abstraction keeps rising, from wiring machines to writing code to simply declaring intent. Programming is evolving from syntax to semantics, from telling computers how to think to telling them what to achieve. At the heart of these advances in the commoditization of computational thinking are prompt engineering and context engineering. Prompt engineering is a new literacy that empowers anyone to harness the power of large language models without needing to write code. Just as programming once defined the how of computation, prompt engineering now defines the what, translating human intent into intelligent action. Prompt engineering comes in two distinct flavors: prompt engineering in the small and prompt engineering in the large. Prompt engineering in the small is about structured, iterative interactions by individuals who use natural language and prompt patterns to reason through complex problems step by step. In contrast, prompt engineering in the large takes that same principle and scales it, orchestrating systems of reasoning that span the entire software lifecycle, from ideation to sustainment. Together, these practices democratize computational thinking, enabling anyone from scientists and engineers to artists and writers to reason and create computationally without ever needing to write code. Context engineering is closely related to prompt engineering. It's the process of tuning the instructions and the relevant context that AI models need to perform their tasks effectively. It's also the design discipline that builds the information hub around an AI system, the structured environment that gives AI models orientation, purpose, and grounding. Rather than crafting a single clever prompt, it orchestrates 5 interconnected spheres, each feeding AI models intelligence from different perspectives. As we just discussed, prompt engineering is the intent translator that converts human goals and nuances into structured, interpretable instructions that shape how AI models reason and respond. Retrieval Augmented Generation, or RAG, is the knowledge conduit. It delivers verified, contextually relevant data from outside sources, ensuring AI models reason with evidence rather than assumptions. Structured outputs are the precision channel. They establish how AI models organize and express their results, such as tables, JSON, or logical formats, so their reasoning becomes traceable and useful. State and history are the temporal compass. They preserve the flow of a session, remembering what's been said and decided, so AI models maintain coherence and momentum within an ongoing interaction. Finally, memory is the long arc. It extends awareness beyond the current session, retaining durable facts, preferences, and prior insights so AI models evolve with the humans they serve. Together, these 5 spheres orbit the central hub of context engineering, transforming a static exchange into a dynamic system of understanding. Teaching students this mindset helps them learn not just to prompt AI, but how to architect the environment in which reasoning itself unfolds. In the age of generative intelligence, context isn't peripheral, it's the gravitational center that holds meaning together. However, since prompt engineering and context engineering are so closely linked, we'll just use the more common term of prompt engineering to refer to both disciplines. There are many benefits from applying prompt engineering, paired with context engineering, of course, that are redefining what it means to think computationally. It breaks down the walls that once separated coders from creators. For example, prompt engineering lowers the barriers to entry for applying computational thinking in both technical and creative fields. Whether you're a poet sculpting words, a physicist modeling the universe, or a programmer designing the next breakthrough, you can now reason computationally without touching a single line of code. It's the great equalizer, a new literacy that transforms imagination into execution through natural language. For the price of about 3 pumpkin spice lattes a month, roughly $20, you can now access advanced large language models like ChatGPT, Gemini, or Claude, and perform prompt engineering at a professional level. Computational thinking, therefore, no longer requires fluency in traditional programming languages. We've moved from imperative programming, languages like C, riddled with accidental complexity, to higher-level languages like C++, Java, and Python, which made things easier but still demanded mastery of dense syntax and semantics. Now, we're entering a new frontier, performing computational reasoning in natural language. You can describe what you want in plain English or any language, and the AI handles the how. This shift from the how to the what is democratizing computational thinking. It opens the door not just for computer scientists, but for social scientists, natural scientists, doctors, lawyers, and national security operators. Anyone who thinks systematically and wants to turn ideas into action. When I was a professor at Vanderbilt, our colleagues from departments like chemistry, biology, and divinity would often come to us in computer science and say, "We'd love to use computation in our research and teaching. Can you show us how?" And our natural response was, "Absolutely. Let's start by teaching you Java or Python or maybe JavaScript." That's when their enthusiasm would fade. They'd smile politely and say, "Maybe computation isn't all that essential to our field after all." But here's the twist. Those same colleagues are now often the first to embrace generative AI. Why? Because they can finally think computationally without learning to code. The accidental complexities of traditional programming no longer stand between them and their ideas. Now, they can go straight from concept to creation, not by mastering syntax, but by mastering prompt engineering. This concludes the second part of my talk on how generative AI is liberating computational thinking from coding. In part 3, I'll show how generative AI is transforming computational thinking by replacing traditional programming with natural language reasoning, allowing anyone to turn ideas into working solutions through prompt engineering and context engineering, thereby redefining coding, creativity, and collaboration.